Okay, let's talk about algebraic and transcendental elements. Algebraic versus transcendental. Uh, Elements. All right. So let's start to start talking about this. We need to fix some sort of ambient setting. So let K contain an F be an extension of fields. Okay, so we say, well, here's the first part. So we say alpha in K is algebraic over F if and only if it satisfies a polynomial equation with coefficients in F. So if and only if, so there exists some a0 plus a1, let's say x plus dot 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 plus ad x to the d. So for some d in f of x such that the following such that the following holds, so that a0 plus a1 alpha plus ad alpha to the d is equal to 0. Okay, so the idea is that it's algebraic. So it is algebraic. So it satisfies some polynomial equation. Okay, so that's what it means to be there. So to be algebraic, and then let me state the other definition, and then we'll give examples. So the opposite of algebraic is transcendental. So if it's not algebraic, okay, so if alpha in K is not algebraic, it is called transcendental. Okay, so let me give you all right, so let me give you some examples. So examples. Okay, the easiest example is alpha is square root of 2. So we could have K being equal to C and F being Q. Right, so then here we can see that alpha squared minus 2 is equal to 0. So there's a polynomial equation over with rational coefficients that it satisfies. All right. All right. So what else is there? So let's take, if we take alpha to be t. So this is where K is C adjoin T, and F is C. Then this is the standard example of a transcendental element. So we actually like adjoin something for the purpose of it not being able to satisfy any relations. So this element is transcendental. Okay. Okay, here's another one. Another example is that so if we do alpha is equal to 1 plus the square root of 5 over 2. So this is the golden ratio. Right? So this is an element of C, and it is algebraic. So this is algebraic over Q. Okay, so how do I know that this one's algebraic over Q? So I guess we need to write down some polynomial for it. So so we have x minus 1 plus square root of 5 divided by 2, x plus, x minus, and then we do 1 minus the square root of 5 over 2. Okay, and so this becomes x squared, and then we add these, so plus, and then we have 1 plus the square root of 5 over 2, minus 1 minus the square root of 5 over 2. Oh, let's see, this should be a minus minus. So minus minus like that. Okay, so then this just becomes, I think, just 1. Let's see, minus 2. So these two parts cancel. So then we have that, and then they multiply together. So then we have something over 4. So then we have a difference of squares, which is 1 minus 5. Okay, so this thing is x squared, and then minus... So x squared minus x plus x squared minus x minus 1. Okay, so this is the golden ratio. It's an algebraic number. This reminds me of something cool. By the way, let's take like a little detour on this. So another way to do the golden ratio is this number, 1 plus 1 over 1 plus 1 over 1 plus... Okay, so this number here is, so you can call this, I don't know, we'll call this gamma. I don't know what you're supposed to call the golden ratio, all right? So you call this gamma, right? And you can see that, so that gamma is equal to 1 plus 1 over gamma, right? So this tells us that gamma squared is equal to gamma plus 1 once I clear denominators. And then this tells us that gamma squared minus gamma minus 1 is equal to 0. So this is also the golden, so this is the golden ratio. So this thing is this is the algebraic number. So this is the golden ratio. So this this infinite let's see, go. So this is the golden ratio again. So this is what's called a continued fraction. All right. So this thing here is what's called a continued fraction. Fraction. Okay, and yeah. So those are examples of algebraic and transcendental. Gamma. So yeah, so these are examples. Oh, dang it. Okay, so let me go back here. Okay, so we have 1 example, 2 example, 3 examples. Okay, that's pretty good. Let me just do like one more. Down. Okay, so let's do one more. Back at black. Okay, so let's take K to be C adjoin T. And let's do F is C adjoin T squared. Okay, so then the element T here, so if I take alpha to be equal to T, right? So then this is also an algebraic, so this is algebraic over F, right? And the way to see that is that alpha squared so another way to do this is that let me show you this. Okay. Okay, so my little pen. Okay. So alpha squared minus, so this is minus T squared is equal to 0. So this is one that you have, but you note that T is not an element of F. Okay. Another viewpoint is that we can just kind of like replace letters everywhere. So F is C of Y, right? And then K is, I don't know, C of T. And then if we have alpha, so then this satisfies this algebraic relationship, so that alpha squared, so here we're using Y is equal to T squared, right? So yeah, so it's like adjoining. So this is another way of writing it, is that this is the square. This is like C adjoin the square root of Y. Okay, so there's an equivalent way. You view this as you just have kind of a formal variable, and one's the square of the other. Okay, so all right. Okay, so So we talked about what algebraic and transcendental extensions are. Now I want to give the definition of a finite extension. So let's do that. All right. So definition. Okay. Oh, let's just do it for field wise now. So, um, let's say this. I got a better one. So a field extension of fields K containing F is algebraic if and only if for all alpha in K we have that alpha is algebraic. All right. I got a phone call real quick. Hold on 1 second. Okay, so I'm going to just continue now. So what I was saying is that there's kind of an issue here. The issue is the following: is okay. So I want a field where every single element is algebraic, right? So if alpha and beta in K are algebraic, right? Is it necessarily true that alpha plus beta is algebraic? Same question for you asked the same question for multiplication, right? So for multiplication, I don't know. Same for. Okay, so if I take two algebraic numbers, is it clear that one of them satisfies a polynomial equation, another satisfies a polynomial equation? How do you get a polynomial equation for the product of them? So here, if you have so alpha is the square root of 2, beta is the square root of 3, then so this one satisfies, we have one polynomial here. So this satisfies the polynomial x squared minus 2. This satisfies the polynomial x squared minus 3, right? So what about the square root of 2 plus the square root of 3? So what polynomial does this satisfy? I mean, it's not even clear from the definition, right, that this would be, I mean, you could take some totally random thing of degree 100. It satisfies a degree 100. This satisfies a degree 1000 polynomial. And if I add them together, why on earth would it be the case that it would be algebraic at all? It turns out that it is, and to kind of get us going on that, there's a very useful notion which is called finiteness. Okay, so I'm gonna do that now. So, and then we're going to use this concept to prove algebricity. So let me give a definition. So an extension of fields. So an extension of fields K containing F is finite, right? If and only if K is finite dimensional as an F vector space. Okay, so this means that that K is finitely generated. So so let me just give some notation here, right? So notation terminology. So in this situation, we call the dimension the degree. I don't know why, but so the degree. So the degree of K over F. So this is this. So this is this is defined to be the dimension of K as an F vector space, and then we use this notation here. Okay, so this is some new notation that we're going to use for dimensions here. Okay, so let's look at some examples. So what are some finite dimensional or finite extensions? So we've done them a lot. So all these quadratic extensions are so q of I over q is finite of degree 2. So here this means that in the fancy new notation that we have qi q, this is 2. Okay, so it's a degree 2 extension. Why is that? So alpha in here looks, so it always looks like, so if I take an element of qi, we've showed before that you can write this as r plus I s for r and s in q. So this is, so the one basis vector, so the first, so this thing here, 1i, so this is a q basis for q adjoin I. So it's a basis for q adjoin I as a q vector space. Okay, so that's the type of thing that's going on. All right. So all right. So let me prove something first, and then I'm gonna go do another little video on simple extensions. Okay, so all right. So let me prove a lemma. Then this is why it's useful, this finiteness thing. So like we were talking about algebraic extensions where all the elements were algebraic, right? So let me give a lemma. Okay. So the lemma is the following. It says, oh, let's go back. It says that if K containing F is a finite extension of fields, then K is algebraic over F. Right, so it doesn't matter what crazy element of K I take, it's always going to satisfy, it's always going to be the root of some polynomial equation over F. So let's do the proof of this. So the proof is as follows. Okay, so it's really easy. The proof is super easy. So it's finite, so let D be the dimension of K as an F vector space. So let's suppose that the degree is K. And so let's take alpha, an element of K. Right, then, so then what we can do is we can just start building too many elements. So the elements, well, 1, alpha, alpha squared, alpha cubed, and so on, all the way up to alpha to the D. So so that this must be linearly dependent. If they were linearly independent, then the dimension would be bigger than D. That would be D plus 1 elements, which are linearly independent. So it must be linearly dependent. So this means there exists, so this is linear dependence over F, right? So there exists some C0, C1, all the way up to CD in F, such that the following holds, right? So you have C0 plus C1 alpha plus all the way up to CD alpha to the D. So we have this is the linear dependence relation. So we have C0 times 1. Okay? And so this proves, this proves that alpha is algebraic now of degree at most D. Right? So we know that it's going to have to satisfy some relation up to D, and so that proves that it's algebraic. Okay, so now I'm going to stop this. I'm going to do a little bit about how to work with simple extensions, and then I'm going to come back to this. All right.